and share screen. Open that up then. All right, so in section 5, we're dealing with um, the inverse operation to exponents. So just to remind you where we were in the last section, we dealt with the properties of exponents, and this section is going to explore the inverse of that. So before I jump too deep into notes, what I'm going to talk about is a little bit of review of some of the math operations that you've done so far in your math career. You'll be definitely familiar with these. Everyone here is going to know that they've dealt with addition and subtraction. You've dealt with multiplication and division. And then the one that we talked about in section 4, one that you've been doing for a while probably, um, even if it's probably the one that you're least familiar with, will be exponents. Okay? And so just breaking down each of these operations, addition is going to add things together. It's finding the sum total of two things together, that whatever those may be. Subtraction is going to find how far apart two things are as far as numbers are. So you subtract, you guys know how to do subtraction. And then multiplication, we're finding out how many times, like how many objects are left over if I multiply groups of things together. That's basically addition of groups, but multiplication is going to be doing that in a single operation. Division does the inverse of that, where it tells me how many groups of a certain number there are. And exponents are going to take some number and tell me how many times it's multiplied by itself. Okay? So again, you're probably more than familiar with all of these. You've done these ever since you've been doing order of operations, probably since middle school, possibly even before. So the one thing I wanted to focus on before we jumped into our section 5 notes was a concept that was really heavily emphasized in Math 1 when you took Math 1. And that was doing the inverse of an operation. So if I have a bunch of operations that are being done in some math phrase, and I want to move objects across an equal sign, I need to do the opposite or the inverse of whatever that operation is doing. So for instance, if two things were being added together and I wanted to undo that, if I wanted to undo two things being added together, I would do the opposite of addition, which is to subtract. If I was subtracting two things and I want to undo that, the opposite of subtraction is addition. Opposite of multiplication is division, and opposite of division is multiplication. Okay? Each math operation has an inverse, something that undoes what just happened. Okay? And that's a critical component to mathematics, is that if I'm able to do some sort of math operation, I should be able to undo it. Okay? I shouldn't like do a math operation and try and undo it and it gives me something completely different. Okay? That would not be mathematics anymore. Okay? And so these inverse operations end up being really critical. And many are familiar with the exponent, and especially when it comes to like squaring something. We've even probably memorized some of your squares at some point in your lifetime. But for any exponent, like we talked about in section 4, whether I'm raising it to the power of 2 or to the power of 7 or whatever, there needs to be a way to undo that operation. And that's what this section is going to focus on, what undoes an exponent. And some of you are already familiar with this, but I'll go ahead and just explicitly say it. It's called taking a root of something. Okay? Taking a root or a radical of something. This symbol that you've all seen before is what we call a radical. All right? It takes the root of something. And so basically the way these are both translated, this is saying whatever object A is, whether it's a number or variable or whatever, it's raised to some power. And that tells me, this number tells me how many times A is multiplied by itself. So if I had A to the third power, my result would be A times A times A, right? This translates as taking now the sum root or some root of this number, and it's saying how many times does some object multiply by itself to give me this number. It's basically the undoing of this guy. So for instance, if I had the third root of A, I would say, I'd be asking myself, what number multiplied by itself 3 times gives me A? Okay, again, this undoes what the exponent does. All right, so the punchline there is to understand that a root or a radical is the inverse or the opposite of raising something to an exponent, and vice versa. So for instance, if I started with the root, the way to undo a root, like a square root, would be to raise it to an exponent. All right, so our section 5 notes are entitled Radicals and Rational Exponents. Radicals and rational exponents. So if you need to, in your notes, again, these are on Google Classroom. Another way to write this term radical, the radical refers to this symbol right here, this square root symbol. That's called a radical. Okay, another term you're going to see often for this is root. So root and radical are both the same thing. It's the same operation. Okay, rational exponent is just going to be another way that we can express a radical, and that's going to be something that we talk about down here in just a second, but I wanted to start with dealing with roots. Okay, so nth root. Okay, again, I use this term nth root to signify that I can take any sort of root. It doesn't have to be a square root. For a square root, I'm asking how many times it's, for a square root, I'm asking what times itself twice gives me a given value. So for instance, the square root of 4, what number multiplied by itself twice gives me 4? Well, 2 times 2 gives me 4. What's the square root of 9? What times itself twice gives me 9? 3 times 3. Okay, that's what a root does. Now, an nth root, it doesn't have to be a square root. It could be like a fifth root. Okay, so if I ask, like, what's the fifth root of 32? What I'm basically asking is, what times itself 5 times gives me 32? Okay, and there's a long way about going into that solution. I'll show you how that's done, but I'm also going to show you the faster way to do that, and that's on a calculator. Okay, so I'll show you exactly like in section 4 how you can do this really quickly on a calculator, whether it's a lame one like mine or some of yours are a little bit fancier, but I'll show you how you can basically plug this stuff in and solve it really quick. Okay, but back to the background information for an nth root, again, is the inverse of raising to an exponent. So I give you 2 different examples here. For instance, 4 squared gives me 16. 4 squared is the same thing as saying 4 times 4, or 4 times itself twice. Gives me 16. So what if I want to undo that? It would be by taking the square root, or the 2 root, even though it's not written there, technically there is a 2 there. Okay, the 2 root of 16. In other words, I'm saying what times itself twice gives me 16. That gets me back to the original 4. Okay, so that's how I can go back and forth within the same family of operations. Flip side of that, maybe not flip side of that coin, but another version of that would be 2 cubed, 2 to the 3rd power. 2 times 2 times 2. That gives me 8, right? That's something that we dealt with in section 4. There's my exponent operation. So how do I undo that? That's what this section was about. Basically, how did I write this as a radical? How do I get this 8 back to that 2? By taking the cube root. Okay, so I have 3rd power, 3rd root. It undoes the same thing, right? So in this case, the way this literally translates is as was the 3rd root of 8. In other words, what times itself 3 times gives me the number 8? Well, that result would be 2. 2 times 2 times 2 would give me 8. And so the cube root of 8 is 2. So that's how I can, again, get back and forth between those 2 values. And again, I'll show you how to do this piece on a calculator. So when you get here, you know how to do it. All right. So that's kind of the background of what a root is and what it does. So now let's talk about this next part of the title, a rational exponent. Rational exponent. Literally speaking, this is how it translates. A rational exponent literally means a fraction exponent. All right. We've already dealt with whole numbers, whether they're really big positive numbers or 0 or negative numbers. That's what we kind of focused on at the end of last week with section 4. But what happens when I get fractions that I'm raising in power to? Okay, it's one thing to say 3 squared. It's another thing entirely to say 3 to the 1/8 power. Okay, there's a very different kind of set of results that we can expect. So a fraction exponent, that's what we're going to explore here. And the punchline here, basically what I want you to understand about what is a rational exponent, when it will be used, is it's going to be the same category as taking the root or radical of something. Okay, so if I had like 5 to the 4th power, and I want to undo that, to do the inverse of that operation, I would be doing 5 to the 1/4 power. Okay, essentially taking a fourth root. So here, this summarizes it pretty well. Here's the punchline right here, that if I'm taking some root of some number, I can rewrite that. These are exact equivalents. I can rewrite this root, this radical, in terms of a fraction exponent. Whatever number is here, whatever number root I'm taking, it's that base raised to that in fraction form. So for instance, this is tends to be the tricky one for students because there is no number written there. It's there, it's just technically not written. It's a 2 root of a, and that 2 root of a can be rewritten as 1/2 power. Okay, a to the 1/2 power. Okay, a cube root, a 3 root of something can be rewritten as that something to the 1/3 power. A 4th root can be written as that something to the 1/4 power, and that's pretty much how it goes. So if I had an 18th root of something and they asked me to rewrite it in terms of a rational exponent, I just take that 18 and shove it under the denominator of that fraction, and now I have whatever that value is to the 1/18 power. So again, there's the punchline of how I translate a radical, a root, into a rational exponent. And they're going to ask you to do this. Your first couple of problems are going to ask you to basically translate between some radical, write it in rational exponent form. Here's a rational exponent, write that in radical form. Okay, and so the flip side of the coin, if you started with this and it said like some value, a, to the 1/7 power, and they're like, okay, rewrite that in radical form. So they want it in this form. Whatever the denominator is, that just happens to be your root. So in that case, it would be the 7th root of a. Okay, so it's not terribly difficult, but this is kind of the main punchline for the start of these notes. Okay, I can translate between writing something in root form to an exponent form. And so when you see a fraction in exponent form, this is a root that you're going to be taking. Okay, and then in here in the margin, just as a little kind of demonstration about why these two things are equivalent, kind of a demonstration for why this works. Okay, so I show you, like, if I were to square a square root of something, that should undo it first off. Squared and square roots are the inverses of each other. Then I should get back to a, right? So something squared is that something multiplied by itself. Okay, and square root of a times the square root of a is the square root of a squared, which comes out to a, right? And you can plug in a number there if it helps illustrate it for you. So if I had like the square root of 9 squared, I'd get back to 9. Okay, just a demonstration. And so why is this the equivalent of that to the 1/2? Well, here's that demonstration right here. We actually learned this property. We learned this property in section 4, where if I have an exponent raised to another exponent, I can just multiply those exponents together. So 1/2 times 2 in that case gets me back to a to the 1 power, or just a. Okay, so again, that's just a demonstration of why these two things are equal to each other. All right, so I just want to go through one example today, kind of show you how this is done on a calculator, which is probably going to be the more important thing that you're going to want to know here. But your first couple problems will ask you to translate between radicals and rational exponents. You'll have another couple problems after that, but they'll give you this kind of information. Okay, they're going to tell you what root you're dealing with, and they're going to tell you what number you're taking the root of, and then they're going to ask you to write that in radical form, like I've done here. That's the easy part. You're just basically using this format, right? N is going to represent the root. A is going to represent the value you're taking the root of. So in this case, the cube root of -27, that would be rewritten this way. So A is just what's ever underneath the radical. N is going to be the root that you're taking of, and you'll get a blank structure and big ideas to fill that in. Just copy and paste what you need. But then it's going to ask you to also evaluate basically what value pops out on the other side of this. So literally this is asking in this example here, what times itself 3 times? That's what the cube root means. It means it's multiplied by itself 3 times. That gives me -27. Okay, maybe you know that off the top of your head, but I'm also going to show you on a calculator. Okay, and your scientific calculators may be a little bit fancier than mine, but again, this will be kind of the important demonstration because ultimately you're going to want to know, like, how do I just solve this? Okay, all right, so in this case, if I want to take the cube root of -27, the thing to understand here is that that's the same exact thing as saying, all right, cube root of negative 27, that's the same thing as saying negative 27 to the 1/3 power. Okay, just using this equivalence right here, right? So I'm going to be able to do that on the calculator. And I want to draw your attention to this button again. Okay, in section 4, we focused on this button to customize our exponent, right? And if I zoom in a little bit closer, you'll notice in yellow here, these secondary functions. Most of your scientific calculators will have these sorts of secondary functions. And so that secondary function there, that x to the 1 over y, is going to be performing this operation here. Okay? And so basically what I'm going to do is I'm going to say, I'm going to take that negative 27. So on my calculator, I have to push this negative sign button to make it negative. Yours might not need to do that. But now I'm going to raise it to the power of 1/3, right? Because that's what the cube root is going to be the equivalent of. All right? But if I were to press this button, it would wait for the whole number answered. And so the mistake might commonly be to push that button, then raise it to the 3rd power. But now it's negative 27 times itself 3 times. It's not what it's asking. Okay, it's doing the opposite of that, the inverse of that. What times itself 3 times gives me negative 27. And so just to show you, I need to press this shift button. For those that didn't know what that did, this gets me to my secondary function. Some of your calculators will say secondary function. When I push that, most calculators will have this little signal right here that tells you, in my case, it says shift. So it tells me I'm working on my secondary functions. Some of your calculators will say second or something like that for a secondary function. Okay, but now that I've accessed that, now I'll push this button and I'll access that secondary function. So now it's waiting for basically what denominator is in here. In this case, 3. So now instead of raising it to the 3rd power, it's taking the cube root of that. And so that result is negative 3. Just to check that result, negative 3 times negative 3 times negative 3, which is the same thing as negative 3 cubed, should give me negative 27. So just checking, negative 3 times negative 3 gives me positive 9. That positive 9 times another negative 3 gives me negative 27. Works out. Let's do one last one to finish off the day, right? In this case, I didn't write it here, but it would be the 4th root of 16. Okay, maybe you can do that in your head, maybe you can't. Again, basically it's saying what times itself 4 times now gives me 16. But again, you have a calculator that can do that function. So I'd start with my base, in this case 16. I can rewrite this as 16 to the 1/4 power if I needed to. That's this little identity right here. But on a calculator, instead of pushing this button to raise it to the 4th power, I'm going to do the secondary function to take the 4th root. There's the 4th root and spits out 2. Okay, so again, just checking that work, that should mean that 2 to the 4th power should give me 16. Okay, and double checking that, 2 times 2 times 2 times 2 will give me 16. 2 times 2 is 4. That 4 times a 2 is 8. That 8 times the last 2 is 16. And we check it out right there. All right, so that's the end of the demonstration today. Before you check out, let me go ahead and stop sharing. I'll end recording.